So we're in chapter 16 of your chemistry book, Oxidation and Reduction, Reactions and Electrochemistry. So you can see what we're going to gradually get into is electricity. But first we need to know what oxidation and reduction, what classifies them into these categories. Well, as you can see in chapter 4, there were 4 different basic types of chemical reaction. There's a combination, when different molecules or chemicals are combining together into making new type of chemicals or substances. Or decomposition. What's a decomposition? When they're uncombining, right? And then there's single displacement, when one molecule or element is displacing another. Or there's double displacement. That's when they're just changing partners. I hope you remember that, because these are kind of foundational when we're talking about chemistry. But also, you can classify into 2 other categories. 2 categories that involve a change in electron configurations of the reacting substances. So they have electrons. The electron configurations are what we're going to be talking about. And those in the former category, which we have, they may fall first into chemical reactions that may fall into 2 categories: those that involve a change in the electron configurations and those that do not. So in oxidation reduction reactions, which we can call redox, that's a short name, redox here, reduction oxidation, we will say redox reactions, have to do with electron configurations of the electrons. So now we know we're going to be getting into what? We're going to be getting into the beginnings of electricity here. So many of the reactions that you'll encounter in life and in the laboratory, a lot of them are redox reactions. So when you think of redox reactions, you're going to think of electron configuration. So let's go on. This first part, chapter 16, section 1, is talking about oxidation and reduction, the process, and what the process is. And there's some principles here. So it says you may be familiar about some types of reactions, such as, think of oxidation, what do you think of? I always think of rusting, like oxygen rusting on iron, or burning gases and oil. Those things when I think of oxidation. And indeed they are types of oxidation. But oxidation, you'll see, is really broader than that. And as for reduction, we talked about reduction iron, reducing iron ore, or the reduction of steel into iron ore, that type. And indeed, but again, when we talk about reduction, we're going to be talking about it in a much, much broader sense than that too. So here we have, let's see, an equation here. This basically here it's talking about earlier we studied the reaction of a metallic sodium with a non-metallic chlorine to form an ionic compound here. So we have 2 sodiums and the chlorine 2 coming together and forming. In this process, an electron from the valence shell of the sodium atom is transferred to the valence shell of the chlorine atom. So here we have a transfer of electrons. And so that's what we're going to be talking about, is transferring the electrons. Each sodium atom lost an electron, and each chlorine atom gained an electron. And so this will come to our definition here. Oxidation. What is oxidation? Any process in which an atom loses an electron is oxidation. And any process in which an atom gains 1 or more electrons is reduction. Okay, how are we going to remember that? Well, I always remember this little saying that they taught long ago when Leo the lion says grr. Why is that? Leo. When you think of Leo, you think of loss. Loss of electrons is oxidation. Loss of electrons is oxidation. Ger is gain of electrons is reduction. Just think of Leo, loss. E, of course, is going to be electrons, oxidation. So Leo, the lion, says Ger. Gain electrons is reduction. So another way I always remember, you're gaining gaining electrons, you think it would be reducing, but it's opposite almost. So gain of electrons is reduction, which is like, you think reduction, you think, oh, it's electrons are reduced. No, it's actually opposite, the gain of electrons. So Leo, the lion, says Ger. Loss of electrons is oxidation. Loss electrons, oxidation. Ger is gain of electrons is reduction. So this is a pretty important foundation that we know this. That's why we have this mnemonic here to help us, because if we don't know that, we're going to be kind of lost, because one is one direction and the other. So loss of electrons is oxidation. Gain of electrons is reduction. So also, reactions in redox may be viewed as acting upon each other to cause a reaction. So one is going to be the reactant. The reactant is going to be the oxidizing agent. And it causes the oxidation by accepting electrons from the other reactant. In the process, it is reduced. The other reactant, the reducing agent, causes the reduction by giving up electrons for the other reactant to accept, and this is called oxidation. Thus, in a redox reaction, the reducing agent is oxidized, and the oxidizing agent is reduced. Just remember, the reducing agent is oxidized, and the oxidation is reduced. It's just opposite there. So when we have a reacting agent, one is the reactant agent, the oxidizing, it's reacting, and the reducing is the other one. It's actually reducing or accepting the electrons, like here, gain of electrons, but this is the reducing. So it's actually opposite in your mind of what you would think it would be. But one is the reactant, the oxidizing agent is the agent that's reacting. The reducing agent is the one that is the agent that is being reduced, or that in being reduced is actually, being oxidized. So it's kind of backwards on what you think. So when I think of oh, okay. So they do an analogy here saying like a dirty sink or bathtub may be cleaned up by using a cleansing agent, but in the process, the cleansing agent does the cleansing. It doesn't get cleansed. Similarly, the reducing agent does the reducing, but it does not get reduced. It gets oxidized. So just know, it says reducing agent, you think it gets reduced. No, the reducing is going to get oxidized. Okay, so let's look at this table here, and that will help us. So these are the terms. So terms involving gain of electrons, and this is loss. This is Leo and Ger. Leo the lion says Ger. Leo is the loss. So here is the oxidation is the loss of electrons, and it's the reducing agent. Even though it says oxidation, it's going to be the reducing agent. And the substance is oxidized because it's oxidation. Reduction, here we have reduction, gain of electrons. The reduction is the oxidizing agent, opposite than you think, because you think it would be over here, but it's the oxidizing agent, and the substance is reduced. So it's just kind of knowing this little here thing is really, really important. And if you know this, also, you'll see loss of electrons. So loss of electrons is oxidation. Gain of electrons is reduction. Reduction is the oxidizing agent, and it's reduced, and the oxidation is a reducing agent. So here we have. So hopefully I described that, but this table is a good one to go back to. So oxidation and reduction occur at the same time, simultaneously, right away. They're just recurring. They don't like take, they may take time, but they're happening at the same time. So whenever a substance loses electrons, some other substance have to gain them, right? So you know that the redox reaction is going to happen. The fact is, it's implied that the term redox reaction is this reaction that's happening. So let's see. One, just to remember, going back here, just to review here a little bit, is oxidation and reduction. As they're recurring simultaneously, one loses and another must gain. Yeah, if one loses electron, it has to gain it. The other side has to gain it. Electrons never just disappear. Oh, they just disappear. No, they never disappear. And as for there's going to be no oxidation without reduction, and there's going to be no reduction without oxidation. They have to go together, and this is what makes the fact of a redox reaction. So now we're getting into something that gets a little more complicated, because it's how scientifically we can classify and put these in our equations, right? So we're going to talk about oxidation numbers. So now in science, they're going to give us numbers that tell us what is happening with the electrons, and that affects and determines the structure, the electronic structure in the reaction. And so then we can in doing this, we can use an oxidation number. So going on, let's see if I can see. Here's a picture actually of a redox reaction of copper and nitrate, and you can see there's a chemical reaction going on. But a lot of times there's a chemical reaction going on and we can't see it. So let's talk about these oxidation numbers. To determine the change in electronic structure that has occurred, we need signed numbers, and these will be our oxidation number. Oxidation number of an atom is the charge the atom is assumed to have in a particular ion or compound, either an ion or a compound. So it's relating to the charges of those electrical charges, I should say, electron configurations, and that's what we're talking about, electron configurations. Assigning valence electrons to more electronegative elements. So in this, we're going to find out which elements are more electronegative. Basically stronger, accepting, as they're accepting electrons, or or should gaining electrons or losing electrons. So negative is an oxidation number. If you have a negative number, that's an oxidation number. And less negative oxidation, less than one number, would be a positive oxidation. So this is just a bookkeeping. Let's read this here. So I kind of went over it, but let's read this part. It says, oxidation numbers are essentially a bookkeeping system invented by chemists to indicate changes in electron ownership. Oxidation numbers also permit redox equation to be balanced more easily than is possible simply by inspection, and may be used to predict reaction products and properties of chemical compounds. A number of rules apply. So basically we're doing this. Why? Because now scientists can predict the properties of chemical compounds. They can look at it there as oxidation numbers on which will react with which, and which would be a strong reaction and what would be a weak reaction. All these things go by oxidation numbers. So here are your oxidation numbers, and I'm going to actually turn here and put these rules, because next this video is going to go over these rules, and these rules are important. See here if I can put them a little bit so you can see them better. Let's see. I wrote them out here. Let's Let's move things over here, and I'll go over these rules, because I think if you go over the rules here, you'll be able to see better. Okay, you can. I cut it in there. There we go. So oxidation rules. Number one rule here is the oxidation number of any element in its uncombined state is 0. So any element, you know, if you take any element in their uncombined state, that means like if you take H2, N2, O2, you know, as an element, or a polyatom, which S8P4, there's only one type of atom. Excuse me, there's only one type of atom there. And so we're just going to give that a 0. So anytime you have like a, you know, H2, N2 alone, you know, standing alone like that, you know it's just going to be 0. Number one rule. So we have 0. So now on to number 2, the second rule here. See if I could get these up right. Okay, there we go. Oh, I'm having a hard time getting these to stand up here. Let me put this here. I have my little sticks here to stand. Number 2 rules. Number 2 rule says as monoatomic. So number 2 rules, the oxidation number of a monoatomic one atom ion is equal to its charge. So as you can see here, we have one combining with another one. So here we have 1 is equal. So here we have to its charge. This is called binary ionic. Basically, you have like sodium chloride, which is salt, and it turns to ion. So you have the sodium comes out, the chlorine comes out, and now you have a charge here. You have a +1 charge of sodium, and you have a +1 charge of chlorine. Or if you take calcium and oxygen and you take them apart, you have calcium has 2 charges and oxygen has 2 charges. So you're going to put those charges. So, and then in other situations, you might have like iron. Iron can be either a +2 or a +3, depending on how it's combined with chlorine here. So it has 2 different types, you know, of iron as combining with 2 different types of electron configurations. So you can see here, you can see right away, chlorine we know is always -1. So basically iron here would be, if you have 2 chlorines, this would be 2. If you have 3 chlorines, this is going to be 3. So anyway, that's another way we can figure out, you know, their electron, if they're positive or negative. So number 3. Sorry, I'm kind of getting this all whacked out. Okay. Number 3, let's just put it here. Hydrogen is +1 all the time. Only exception is if it's like at the end where you have a picture here of lithium hydrogen, then it'd be -1. But hydrogen usually, number 3, if you're going to count hydrogen, you're going to count it as a +1. Number 4, oxygen is -2. So oxygen is always going to be -2 unless you have a peroxide. And a peroxide here, you have H2O2. Because the oxygen is combining in another sense, you'll end up with a -1. So just think peroxide. And then fluorine here, of course, when oxygen is in the front there, you have 2. So those are just exceptions, but most likely in all of the equations that we're going to present right here, oxygen is going to be -2. Okay, let's move this back here so you can see the other. Okay, move this down here. How about that? see it better. Okay, number 5. Get into number 5. Halogens. Halogens are, halogens, they are the ones that are bond to oxygen or iodine. They're in the periodic table in column 17. And halogens are like, what do I have? Fluorine, chlorine, bromine, iodine. All of these are common halogens. And they're going to always be -1. Unless they're bound to another halogen or into oxygen. So if you have two halogens are bound together, they're going to be bound together in a weird configuration. So, but if a halogen is bound to any of the columns in column 1 or 2, you think of halogens you think of sodium chlorine. Chlorine would be a halogen. Iodine would be a halogen. So unless bound, halogens are going to be -1. So kind of important. So we have hydrogen is +1, oxygen is -2, and halogen is going to be -1. So when you go through and you see a halogen and you know that, okay, these halogens, they are going to be -1, you look and see if it's combined with another halogen, and you know, okay, that's not the case. But if a halogen is combined with anything else, especially in columns 1 and 2, with the alkaline metals and the earth metals. So let's bring that up here. See if you can see this. Right here. Alkaline metals are group 1. Alkaline earth metals are group 2, and aluminum. And these are equal to the valence electrons in their neutral atoms. So you look at how many valence electrons these have, and it'll be equal to that. So that's how we're going to figure those out. But the most important is this last one. The algebraic sum, number 7, of oxidation on all atoms and their molecules and their polyatomic ions must equal the charge that the particle has. So, and this is where we're going to do all our figuring out configuration to figure out what they are, is that we have to use we're going to use algebra to do it. All right. So hopefully I went over that okay. So let's go over the rules right here in your book real quick. So rule number 1, oxidation number of any element in uncombined state is 0. Number 2, the oxidation of a mononic 1 atom, like sodium chloride, and its charge, so that is going to be, the sodium would be +1, -1, calcium would be +2, so you know that. So that's that 1 charge there. Hydrogen is going to be +1, oxygen is going to be -2, halogens usually are -1, and the alkali metals and alkaline earth metals, group 1, group 2, group 13, in their compounds, they have a positive oxidation number that's equal to the valence of their electrons in their atom. And so potassium would always be +1 and calcium would be always +2. So that's when they're alone. They can't be combined with anything. So, and then of course, when you're combining and you have a molecule like this, chromium oxide here, so basically he says for neutral uncharged particles, such as the molecules of water, the sum must be 0. For charged particles, such as chromium oxide, the number should be equal to the charge. So basically here you have to have, it says 2 negative, so it's going to be -2. And this is how you're going to calculate your oxidation number. And this gets a little bit complicated, but actually it's kind of fun to do. So let's go on to the process here. Oh, here's the summary of the rules. This is a good to go by here. The summary of the rules for assigning oxidation numbers. Here we go. Number 1, oxidation number of any uncombined element is 0. Oxidation number of a mononic ion, is equal to its charge. So hydrogen is +1, oxygen -2, halogens are -1. Alkali metals, whatever valence they have, they're going to be their valence. But if they're combined with another molecule, then we have to figure out what their valence is in their combination. And that's what we do in doing algebra to find out what the valence are. So basically just knowing these in your mind is very important. And if not, go back to this table. So now we're going to go to the examples. Okay, I have the examples. I actually did see if I can present this to you better. Maybe right here would do. Okay, well, here we go. I'm having a hard time with this, so I'm just going to leave it here. So here we have this C207. Yeah, maybe I'll just bring it up here. So you have C207 is basically the rule is oxygen has 2, right? So the first thing you're going to look here is that oxygen has the oxidation number of 2. That is rule number 4. So we must calculate the oxygen number of chromium. Because this is combined, we can't just figure out what chromium is, so we have to combine it, and then the answer, the result has to be a -2 ions. So we must calculate it if we let X, or algebra X, equal chromium, and set the sum of oxidation numbers to equal the charge. So what we do then is that we're going to take chromium and just put it as X. And of course we know there's 2 atoms of chromium 2. So 2 atoms of chromium, and then we have how many atoms of oxygen? 7 atoms of oxygen, and each atom of oxygen on rule number 2, remember oxygen's always -2. So we put basically 7 atoms times -2 is what? -14. So that on this chromium then, we don't know what it is, we know there's 2 of them, so we put 2x plus or minus, plus minus 14. So we take that, of course we're going to add 14 to this side, and we're going to get 12. So we have 2x equal 12, and then of course we're divided by 2, and we get 6. So x is going to be 6. So we know chromium is going to be 6. So then we put down chromium as 6 here. Then we have oxygen is -2. So we know what this is. And if you take 6 times 2 is 12. And then you're going to take a negative, you're basically taking a negative, you got 12, and you're taking the -14, but you have 2 of these, yep, so -14, but you're going to end up with a -2 charge, right? So it works out if you check it. So anyway, that's the first one. So let's go on to the second one, this copper with the nitrate here. So we have copper here. And so we're going to do this one. Figure this one out. These are not really hard to do. They're just a little bit of algebra. So here we have copper nitrate has 2 nitrate ions right here. Here's the 2 nitrate ions. And the copper cation, basically copper, you know, and we find out the copper cation must be copper 2 because there's 2 nitrate, which are -1, and the copper. So to balance these together, we have to have the oxidation number, rule 2, of +2 for the copper. So the oxygen is going to be -2, that's rule 4. So we know the copper is going to be +2, the oxygen is going to be a -2. But now we don't know what nitrogen is, or the nitrogen in the atom. So we have 1 atom of nitrogen, but we're going to count it. We're not going to count that 2 yet. So 1 atom of nitrogen, and we have 3 atoms. 3, we're just talking about NO3. We have 3 atoms of oxygen. So 1 atom of nitrogen is going to be our X. It's going to be the one we're trying to find. 3 atoms at a -2. 3 times -2 is -6. When you add these 2 together, you have to get -1. What, in the midst of -1. So x plus -6 equal -1. So you're going to say x equals 5. So, so in the midst of the -1, we know that it has two -1 nitrate atoms. So you know it's going to be -1. That's where I got the -1 here. So that's the confusion right there. That's nitrogen in the ion, and you can check it. Here it has copper's going to have 2, and we have nitrogen as 5 plus 5, and oxygen as -2. And if you add this whole thing up, you're going to end up with that oxidation number, being, or let's go back to where, being equal here. So here we go. So anyway, it's just how we're going to put these together in the midst. This one's a little bit difficult, probably the more difficult one to do. But anyway, so I'm going to stop there, and then we're going to go on to the next section.